So in the last video, we introduced the idea of quantum mechanics and how this is the best theory that we have today for mathematically modeling everything that we can see in the world. What we didn't talk about was exactly how it was developed, where it comes from, what the foundation of quantum mechanics is. Well, the foundation of quantum mechanics was built by a guy named Erwin Schrödinger, who developed what we now call the Schrödinger equation. And this is what it looks like in its very much simplified form. It's not actually just four things here. These are actually three things, because those are both the wave function. But what this is we have the Hamiltonian, we have the wave function, and then we have the energy of the electron. Now, it looks a lot simpler than it actually is, because there's actually a ton of math inside of each of these things, with the exception of the energy. The energy is just an energy value. But the Hamiltonian, the wave function especially, there's a lot of stuff inside of those that we've just simplified down to a single symbol. But what this equation allows you to do is it allows you to find solutions for the wave function of an electron. Because remember, we said that light as well as electrons and truly everything actually has both particle nature and wave nature. Sometimes it behaves like a wave, sometimes it behaves like a particle. This is mainly only true for very, very tiny things like electrons. And so if we want to find the wave function, the actual mathematical function that describes the wave nature of the electron, we can use Schrödinger's equation to do that. Not only that, if we take that wave function and we square it and we plot it versus distance, what we get is a 3D representation of the volume of space where we are very likely to find the electron. So we actually have a map, in a sense, of where the electron is likely to be. This is what we call, this represents the orbital. This is where the electron is likely to be found, is inside that orbital. Now, when we're looking at the wave functions here that describe the electron and where it is inside of the atom, the wave function tells us the size of the orbital where the electron is, it tells us the shape of the orbital, and how it's oriented in space. And more specifically, inside of that wave function, there are four terms, four integer values. Well, technically only three of them are integers, and the fourth one is a fraction, but the wave function looks something like, just kind of blah, 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 and then there'll be a 1, and then blah, 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 and then a 0, and blah, 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 maybe a 1 again, and then a half. And so these four values that you find inside of the wave function, those four values specifically help determine the size, shape, and orientation of the electron's orbital inside of the atom. And so because these four numbers are so important, they get special names. We call these quantum numbers. So these quantum numbers, which I have three of them listed there, and we're going to see the fourth one actually. Let me see. Yeah, there it is. So these are the four quantum numbers. We have the principal quantum number, the angular momentum quantum number, the magnetic quantum number, and the spin quantum number. So these four things tell us where in an atom an electron is, how it's positioned, which direction it's pointing, all that good stuff. So more specifically here, the principal quantum number, which is usually represented as n. So if you had a principal quantum number of 1, usually that would be written as n equals 1. So it's just the n number saying what that principal number is. This tells us the shell that the electron is in. This is the broadest categorization, the biggest classification that we can give something. The angular momentum quantum number tells us the subshell that the electron is in, and it is usually represented as an italicized lowercase l. I know that kind of looks like an emoji flipped the wrong way, but that is usually represented as lowercase l, like that. So if we have an angular momentum quantum number that is 0, that would be L equals 0. The magnetic quantum number is m sub L. This tells us the specific orbital inside the subshell that the electron is sitting in. And then the last one is the spin quantum number, and it tells us whether the electron is spin up or spin down. It's probably the least important of the four, and it can only ever be 1/2 or negative 1/2. Those are the only two numbers that it can be. Now, if you're thinking to yourself right now, what the heck is this guy talking about? Throwing quantum numbers at me and angular momentums? I don't even know what angular momentum is. Well, let's try to simplify this. Essentially, what these quantum numbers are a filing system. These numbers, these quantum numbers that every single electron will have, every single electron has its own individual set of those four numbers, and those four numbers are like a filing system for a warehouse, only our warehouse is the atom that the electron is in. So if you've ever worked in a warehouse before, or if you can even imagine working in a warehouse, which I hope you can, if you have some big warehouse like this, if you're tasked with finding a specific box in that warehouse, things are not going to go terribly well if there is not an organized system inside that warehouse. If your boss comes to you and says, "Hey, I need this box," and you say, "Okay, where is it?" and he says, "It's over there." It's not going to work very well. It's not going to work well at all. You're not going to be able to find that box. Every warehouse that was made and designed with any kind of intelligence at all has a system, has some kind of system for where everything is, so that you can find things quickly and easily. So perhaps in this warehouse, they have each of these rows numbered. So maybe this is number 1, and this is 2, 3, 4, and so on. So they have each of the rows numbered. So maybe if you're trying to find a specific box in there, you're given a set of numbers, and each of those numbers tells you something about where the box is. The first number might tell you the row that the box is on. So maybe your box is on row 2. And then maybe the next number tells you the specific pallet that your box is on. So maybe on each of these rows there's another numbering system, where as you go down the row you have maybe A, B, C, D, just to vary the numbering system. And so maybe you have 2A, and then I know the pallets aren't very tall here, but let's pretend like there's stacked pallets. So maybe the next number tells you how high on the pallet your box is. So if it's on the floor, or if it's, if it's maybe this number is number 7, that tells you, okay, it's pretty high up, I should bring a ladder to get that box, because I'm not going to be able to reach that. And then the last number just tells you on that specific shelf, if you will, on that pallet position, which specific box you're looking for. And so maybe we have a last number here, or maybe it's a symbol of some kind, and we'll say it's blue. I don't know. Just trying to vary up the classifications here. And so with these numbers, or letters, or whatever it is, this classification system, you'll be able to tell, okay, I'm going to go to row 2, I'm going to go down to pallet A, I'm going to go up to the 7th shelf on this pallet, and I'm going to get the blue box. And so there is a system that tells you exactly where something is in the warehouse. And this is exactly what the quantum numbers are. The quantum numbers are just a way for us to identify where in the atom the electron exists, where it exists in the atom. because electrons can only exist in very specific places. If you remember our previous discussion earlier in this chapter, they can't just be, to go back to the warehouse analogy, we're not going to have just boxes laying in the middle of the floor. They can only be in very specific places. And so we can use these quantum numbers to work out where all the electrons are. And also, just as importantly, where they can't be. Because again, there are only very specific places they can be. So, when we are looking at our atom, like our warehouse here, the way the atom is situated is that the smaller the principal quantum number, the principal quantum number would kind of be like our row number from our warehouse analogy. The smaller that principal quantum number is, the fewer the angular momentum quantum numbers you have available, which would be the subshells, which would be like the pallets from our warehouse analogy. So as we go to larger principal quantum numbers, more and more of these subshells become available to us. So each of these rows here is a shell. So we have the first shell, second shell, third shell, and fourth shell, and these are getting progressively farther away from the nucleus of the atom. And so as they're getting farther away from the nucleus, there's more space for them, and so you can fit more of these subshells into each of the shells. Excuse me. In addition to that, in each of these subshells, as we go from one to the next, we have more space in those for the individual orbitals. Which, let me see, do I talk about that later? Yes, I do. Okay, so each of these subshells has its own classification. Technically speaking, they have numbers as well, but usually these are referred to as S, P, D, and F. But they do, like I said, they have numbers as well. But we're going to go ahead and stick with S, P, D, and F. So the principal shells are numbered just 1, 2, 3, 4, and so on. We're probably never going to go above 5, maybe 6. But we're going to mostly stick with 1, 2, 3, and 4. And then each of these subshells, the first one is called S, the second is called P, third is D, and the fourth is F. And inside of each of these, we're going to have the individual orbitals. So if we look at the S subshell, these have a shape like a sphere, just a perfect sphere. So the first S subshell we come across is the 1s. When we're numbering these, we always put the letter after the principal shell number. So on the first shell, the 1 shell, we have the S subshell, and it is a small sphere. The 2s, so that's again the same type of subshell, but now we're into the second big shell, if you will. That is the 2s. It has the exact same shape. It's just a bit bigger. But the shape is exactly the same. And the same is true for 3s and 4s. We're just going to a larger shell, and so the subshell is going to be bigger. Oh, and by the way, each of these S subshells has one orbital in it. So you have one orbital inside of there, and each orbital can hold 2 electrons. So every orbital we're going to come across can hold 2 electrons. This is where that fourth quantum number comes into account. So if the box here is our orbital, we can have 1 electron that is spinning up and 1 electron that is spinning down. But we can never have 2 up or 2 down. They always have to be opposite. So every orbital has 2 electrons in it, or at least has the capability of having 2 electrons. technically doesn't have to have 2 in it. If, for example, you have hydrogen, hydrogen only has 1 electron, so it's not possible for it to have 2 in an orbital. So the maximum that an orbital can hold is 2 electrons. The p subshells, which is the next one up after the s, these have a different shape. They're more dumbbell-like shapes, where you have kind of 2 balloons that are touching in the middle. And the p subshell doesn't have just 1 orbital, it has 3. As we go from one subshell to the next, we are always going to add 2 orbitals. The easiest way I know to think of it is, we have 1 orbital here, that's the s. When we go to the p subshell, we're just going to add an orbital on each side. So that's the p is with 3 orbitals, and then when we go to d, as we'll see in just a second, we add 2 more. And so the d is going to have 5 orbitals in it. I'm not saying here, by the way, that the s is inside of the p. They are completely separate orbitals. I'm just trying to give you a good visual cue here to remember that we're always adding 2 orbitals when we go from one subshell to the next. So because this subshell has 3 orbitals in it, the p subshells can hold up to 6 electrons. Because again, every orbital can hold 2 electrons. So the p subshell can hold 6 at a maximum. The last one we're going to look at here is the d subshell. This has 5 orbitals, like we mentioned just a second ago. If each of those hold 2 electrons, that gives us a maximum of 10 electrons in a d subshell. Now the shapes of these are kind of similar to p, but we have 4 lobes instead of 2, with the exception of the dz squared, which is a weird one. But other than that, they all look very similar to p subshells, just with essentially doubled. All right. So when we are writing what we call electron configurations, and an electron configuration is just it's our way of describing where electrons are in an atom. We have kind of 2 main methods that we can use to do this. There's what we call just a simple electron configuration, but then there's also what we call the orbital diagram. Now the electron configuration doesn't give you as much information, but usually the electron configuration is more than enough. Usually that's all you will need. But we will still be doing orbital diagrams because it's good to know how to do those. And it's if you write the orbital diagram, you actually are describing all 4 of the quantum numbers with what you write. And so I think we'll go ahead and pick up with these next time. If you're still really confused about what we're doing here, don't worry. That is the normal, sadly, the normal response to this section of the chapter. It should make a lot more sense, or at the very least, you should understand what you need to do a lot better after the next video. But I want to go ahead and cut it here because otherwise this will be a 45-minute long video. So we'll go ahead and stop it now, and in the next one we will actually talk, practically speaking, what am I expecting you to be able to do with these quantum numbers and electron configurations. So I will see you in that next video.